Hey there, teachers and students. My name is Benjamin, and I teach teachers the skills they need to pass certification exams. This is my series covering the TExES Math 7 through 12 exam for certification in TExES. This is going to be part 1 from Competency 1 described in the Pearson exam framework, the statements for which you can read down below. But Competency 1 requires the teachers to understand the real number system. So the first topic we're going to discuss are the number categories. Now, what you're going to see here first and foremost is a very important graphic organizer to help you understand the real number categories. You'll see a large circle labeled rational numbers, okay? And inside of it, there's going to be 3 other circles, which we are going to label integers, whole numbers, and natural numbers. The smallest set is natural numbers, and all natural numbers are whole numbers. Of course, then all whole numbers are integers, all integers are rational numbers, and all rational numbers are real numbers, and that's why they're shown as bubbles inside one another. The set of natural numbers is defined as all of the counting numbers starting from 1. So I could say 1, 2, 3, 4, 5, and so on to infinity. These are all of the natural numbers. Then if you want to move to a slightly larger set called the whole numbers, it is the exact same set as natural numbers, except we actually include 0 in this one. So it's the counting numbers, but we start from 0. Okay. If we want to move on to a much larger set, the integers, that's going to be all of the natural numbers, their opposites. So counting -1, -2, -3 in that direction to negative infinity, and as well as including 0, this is going to be the entire set of integers. And then we can go ahead and continue to a much larger set, which is called the rational numbers. And it's going to be all of those integers and also all of the fractions of those integers that we can show in between each integer. So, for example, 7/8, 3/4, 9.5, all of these terminating or repeating decimals, or any numbers that can be written as a fraction in between integers, including all of the integers, this is what we call a rational number. So then, if you look over to this white circle, you'll see a bubble that says irrational numbers, and you'll see numbers like the square root of 10 and pi, and then also some decimal number that looks like the decimal numbers keep going, and then you get an ellipses at the end of it. That's going to be called a non-terminating decimal. And the reason why these numbers are here in the white bubble is simply because there is no way of writing them as a ratio of 2 integers. In other words, you cannot write them as a fraction. So there is no integer that I can write in the numerator, like a, and another integer that I can write in the denominator b that could ever possibly equal to the square root of 10. It just won't work that way. You can never have some fraction a over b be equal to pi. And you can never have some fraction a over b be equal to some decimal number that will go on forever and never repeat or also never stop. So these kinds of numbers that cannot be written as fractions, impossible to write them as fractions, we call them irrational numbers. So it has to at least be able to be written as a fraction in order to be called a rational number. Of course, they are all still real numbers, and they're all inside some category of real numbers, and our goal is to make sure we put them in the smallest category possible. So if someone said categorize the number 2 for me, right? The number 2, you see it here in the natural numbers. Well, it is irrational. It is rational. It is also an integer. It's also a whole number, but the smallest set that it belongs to is the natural numbers. So if they said to categorize it, you would most correctly say the natural numbers. It belongs to the set of natural numbers. Now, what kind of questions might you be asked on the actual TExES exam? Well, I have a really good example for you right here. It says, which of the following 10 numbers are irrational? Well, okay, let's go ahead and take a look. And if you need your graphic organizer with you, that's absolutely fine. Let's look at the first number here, 0. Okay, well, we discussed the fact that 0 is the only whole number that's not also a natural number. But if we're even discussing them being natural or whole, then we know that it's rational. So we cannot say that it is irrational. Okay, now I'm going to go ahead and go on to the next number, 10. 10, of course, is a counting number. If you start from 1 and you go on to 2, 3, 4, 5, you'll eventually get to 10. Therefore, it must be natural, and therefore it must be rational. So it is certainly not irrational. Now, we actually discussed pi specifically. Pi is just one of those numbers that you have to remember is irrational. You can list out a few of the decimal numbers, but in reality, the perfect answer for pi is a decimal number that will go on forever. It will never repeat in sequence of its decimal numbers. It will never stop. So we say that pi is indeed irrational. Okay. The next one is negative square root of 80. All right, so there's a trick here. And let's go ahead and write this down here on the screen so that maybe you can write it down for your notes. There's something you need to remember, and it's the reason why you see so many square roots here in the irrational numbers bubble, okay? The square root of non-perfect squares are always irrational. Now, what do I mean by non-perfect squares? Okay, this word non-perfect squares. How do I know if it's a non-perfect square? Well, if we're talking about a perfect square, okay, a perfect square is a number where if you take the square root of it, then you get a natural number. Okay, well, I'll give you some examples here in a second. A perfect square would be something like 16. The square root of 16 is equal to 4, and 4 is a natural number. Another perfect square would be 81, because the square root of 81 will give me 9. But if I'm looking at something like the square root of 10, well, there's a perfect square close to 10, it's 9. The square root of 9 will give me 3. The next perfect square is 16, but the square root of 10 does not give me a natural number. And if I'm trying to take the square root of some number that is not perfect, then what's going to happen is I'm going to get an irrational number. I'm going to get a number that will never be able to be written as a fraction. So I will always say that the square root of non-perfect squares are irrational. That's just something you're going to have to remember. And as you can see here, if the square root of 81 is perfect, right? The square root of 81 is 9. Then the square root of 80 is not going to be a perfect square. It's not going to give you a natural number. So we're going to say that even the negative square root of 80 must be irrational. So I'm going to go ahead and circle it. All right. So let's move on to 11%. 11%. What do I do with percentages? Well, percentages can always be written as a fraction. All you have to do is take that number and put it over 100. Okay, so if I have 11%, that's going to be equal to 11 over 100. Okay, and even if there's a decimal in your percentage, like let's say, for example, it was 11.5%. Let's say, for example, it was 11.5%. I'd still put that over 100. And I would just multiply the numerator and denominator by 10 until I no longer have a decimal. So this would actually be equal to 115 over 1,000. And no matter how many times I have to multiply it by 10 to get the decimal out of there, it's still going to be a fraction. So then it must be rational, not irrational. All right, so I'm going to mark that one out. All right, so now I have another number here, 2.5 with a little bar on top. All right, this is going to be an important one to look at. 2.5 with a little bar. What does this little bar mean? All right, it's really simple. It means it's going to be basically equal to 2.555 repeating forever. But the thing is that we don't actually put an ellipses here because we know exactly what is going to continue to repeat. It's going to be 5 forever. And so what we call this here is a repeating decimal, and repeating decimals are considered rational because we can write repeating decimals as a fraction. All right, so this one is going to not be irrational. Good. So let's move on to this next decimal. Now, a key thing to pick up here is that you already see an ellipses here, and if you see an ellipses written a decimal that ends with an ellipses at the end, you already know that it's not repeating and it's not terminating. So don't let all these 6s and 1s confuse you. Okay, there is not a common pattern that's reoccurring exactly as it was before at any point in this decimal system, 61661, 6661. Okay, even if you might be able to guess that the next 5 digits would be 66661, that's not the exact same set of numbers. It's a new set of numbers with one more 6 than before, so it's not repeating. Okay, so just if you ever see that ellipses there, then you can pretty much know for sure that this is irrational. I put a box on it, but we're going to go ahead and say that this is irrational, so I'm going to circle that. All right. The next one is easy. It's already written as a fraction for you. The literal definition of rational numbers are, can they be written as a fraction? So we know for a fact that this is not irrational. All right, let's go ahead and move on to negative 9.345. The fact that this decimal number doesn't end in an ellipses means that it's terminating after the 5. There's no more decimal places, so it must be rational. And then finally, we have the cubed root of 1 over 27. Now, this is a little bit more of an advanced expression. So let's go ahead and rewrite it in a way that is a little bit easier to see. We could say that this is, in fact, also the equal to the cubed root of 1 over the cubed root of 27. Of course, 1 times 1 times 1 is equal to 1, so we can easily say that the cubed root of 1 is just 1. And then, is there any number cubed that gives you 27? Hopefully, you can pull it out of your head pretty quickly. This is a pretty small number. You might think like, okay, 3 times 3 is 9. Times 3 one more time is 27. That's true. So then we could say that the cubed root of 27 is 3. And what we have here is just some fraction 1 over 3. It's written as a fraction already, so we can say for sure that it is rational, not irrational. So I'm going to mark this one out. So mark this out here as well. So what you see here is that we only came out with 2 of these 10 numbers that are irrational, but it's a really great example because we got to see a lot of different kinds of numbers, and we got to discuss whether or not they are in fact rational or irrational, and why they are in fact rational or irrational. All right, that's all for this topic. If you have any questions or need further practice, don't hesitate to get in touch with me via the email address listed below. Also, smash the like button for me if you don't mind, but more importantly, share this resource with other teachers who might need it. I'll see you in the next one.